Okay, so let's start. On Tuesday, we were talking about expander mixing lemma. And basically, what it says is that when your graph have small sigma 2, when sigma 2 is like sigma 2 is the maximum of lambda 2 and lambda n. So when sigma 2 is small, so both of these, like all of the eigenvalue in absolute value are small, then you have that for any two set, the number of edges between the set is similar to how it looked like in the D product graph. Okay, so that's expander mixing lemma, and this is like the property that is kind of quite strong. It's stronger than just expansion. This is like measuring how many edges are there between two sets and not just one set up. Like just look at one set and look at the number of edges out of the set. Okay. And so we were talking also about Ramanujan expanders. So can someone remind me what is this? Yeah, the graph such that basically sigma 2 is smallest possible. So it's a D regular graph. Such that sigma 2 is smallest possible, which is something like this. There is some, actually, if you want to be precise, something like this. Yeah. And this is tight, like you cannot be much smaller than that. Yeah. And note again that if you want the graph to be expander, just knowing that sigma 2 is strictly less than 1, that is already means that your graph is an expander. But for this guy, it's like much smaller than 1. So this is basically the Ramanujan graph is the best eigenvalue expander. So what about lossless expander? Can someone recall what is that? I mentioned briefly at the end, actually. Yeah. So it's a D regular graph such that the conductance is the best possible. So not 1/2, but very close to 1. It's quite important to be more than 1/2, basically. They exist, yeah. Yeah. For example, if you take a random graph, you would have this. Like if you take a random graph where, like, when D is like, when maybe D is like epsilon square or something like that, 1/epsilon square, then can prove this. And but yeah, it's kind of open. Like a lot of things are open. I'm not super sure what are still open, but it's a very interesting object as well. And today we will talk about an application of Ramanujan graph. I'm not sure if maybe at the end of the class I might talk about application of lossless expander. But yeah, this application is easier to talk about. And the application is about the problem called vertex connectivity. Very classical problem. So the problem is just that you are given a graph, and you just ask how many vertices you need to delete from the graph so that the graph is disconnected. So, so suppose that your graph look like something like this. Then if you delete just one edge or one node, then the graph will not be disconnected. But if you delete two, then you can disconnect the graph. So we ask for the minimum number so that you can make the graph disconnected into two component. Okay, and we will just, in this lecture, we will just think about unweighted and underweighted graph. But this problem makes sense for weighted graph too, where you basically want to find the set of vertices with smallest weight, total weight, and you disconnect and you delete them. So to disconnect the graph. You can talk about directed graph too, but yeah, it's not today. And the first thing we need to talk about is just the notion of vertex cut. This is nothing but it's just a partition of vertices into three parts. So suppose something like this. And I call the part, one side is L. Here is like a separator. And this part is R, on the left and on the right, and something in the middle, which is separator. So if both sides L and R is non-empty, and there is no edge between L and R, nothing like this, then we say that LSR is a vertex cut. So basically, if you delete S, then the graph disconnected. Okay. And the size of the vertex cut is simply the number of nodes in S. So yeah, so we can basically, now the problem can be rephrased as, what is the size of the minimum vertex cut? Okay. And this answer, this number is basically called vertex connectivity of a graph. And it is usually denoted by kappa of G, or just kappa. Okay, we see a picture already. Okay, and from now we just said that vertex min cut. LSR is a vertex min cut if it's a vertex cut of minimum size. That is, the size of the cut is kappa. And now S, this set here, we will say that it is a ST separator. When you delete S, then S and T are disconnected. When you delete a capital S, then a source and sink are disconnected. Okay. And so basically, let me denote this by kappa between S and T. This is just the minimum ST separator, or minimum vertex cut, such that it separates S and T. And we know, right, that this thing, you can compute it using MaxFlow. Why is that? Because basically, the minimum vertex ST cut is the same thing as maximum number of vertex disjoint ST path, or vertex it's like vertex MaxFlow between S and T. So yeah, I will just, if you don't kind of familiar with this, like you can look it up, but just for today's class, we just assume that to compute kappa from S and T, between S and T, kappa ST, you can just call one max flow. Okay. And just from the definition, we can see that vertex connectivity of a graph is literally just the same thing as you minimizing over all SNT and kappa of ST, because you basically want to disconnect some pair SNT, yeah, and you're minimizing over all pairs. And just from this, it's kind of clear that you can compute vertex connectivity using n square max flow, because just take like all pairs of vertices, compute kappa ST, and take the minimum number. That's your answer. Okay, so that's like an easy algorithm, and obviously like we want to ask how fast can we do, how much faster can we improve this. And so actually one can improve upon n square. So if kappa is very small, it turns out that there is an algorithm that just take n kappa max flow, and we will maybe talk about this tomorrow, but or you can think about it too. But this is not like a strict improvement, right? Because kappa can be as big as n half or like close to n. So this is still like n square in the worst case. And today we will see that we can do it in basically n to the 1.5 max flow. But there is one caveat actually. That is, I would assume that the graph is not too extreme. That is, let me denote this. Let delta denote the minimum vertex degree in the graph. I will assume that there is at least just one node with degree like strictly smaller than n, like 0.9 n. So if this is not the case, there will be some way to handle this and get something better than n square max flow. But just for today's class, I assume this thing. Okay. Yeah, and this is based on the paper by Gabao. So that is for today. And but I want to, before talking about the algorithm, just want to mention the state of the art. So the algorithm here is deterministic, and that's important. It's still the best known, basically. This is like the state of the art already for deterministic algorithm. But for randomized algorithm, just very recently, my co-author and me improved the state of the art to just polylog max flow. And basically, for each max flow, maybe you can just assume that max flow can be done in near linear time for simplicity. But because at least we kind of believe that it will be done, it will be near linear maybe in 10 years. Right now, it's not yet. It's not near linear yet. The best max flow, best time right now is there are two algorithms. One is this time, but this assumes that unit capacity. Another one takes this time in general. So this is the best max flow time algorithm. So you see that like, and I ignore like polylog. Yeah. You see like, at least when the graph is dense enough, there already exists like a linear time, near linear time max flow. So maybe the way you think about it is that max flow can be done in linear time, and you just count how many max flow you need. Okay. So for randomized one, you can do it with a very small number of max flow already. But the deterministic one, this is the one by Gabao here. So the running time that is stated is a bit messy. The running time that is stated in the paper is a bit messy, but really what is happening is that, yeah, it's going to be something that I'm going to present today. Like small, like n to the 1.5 max flow. Yeah. And actually, this is like the only fast algorithm that I know that explicitly exploit Ramanujan graph. Maybe there are more examples, but yeah, this is the only example I know. Okay. So now we go to the algorithm. Okay. So let's look at the easy case. The easy case is when when the cut is kind of balanced. And just to be clear, I will say that the vertex cut, LSR, is beta balanced if L is bigger than beta. And I assume always that R is quite big. Like R is on the larger side, and L is on the smaller side. And so when I look at the vertex cut, maybe this. So in today's discussion, I always assume that when I say LSR, R is like not too small, okay. Because so know that maybe I should say this first. So let me do this first. I assume, right? We assume that delta is not too small. It's not too big. It's not like everything. Then, actually, from here, we know that the size of the vertex, the minimum vertex cut, must be less than delta 2, which is less than this. Why?
The minimum vertex itself is the minimum cut.
Yeah. Yeah, you can just take the guy with the minimum degree, V, and then you delete everything else, like all of his neighbor. So that's like one vertex cut. So you have this. Okay. So we know also that the size of the minimum vertex cut here. So let's say that L star, S star, R star. If this is a minimum vertex cut, this thing is less than this. And so it means that the bigger side, like if I assume that R is on the bigger side, this is like a still of size O of n. And I just talk about now, like I said that L, like this cut is beta balanced. I just talk about the cut of the size of L. Okay. So LSI is beta balanced if L is bigger than beta and R is big for sure. And you should think of beta as maybe square root n. That's the parameter that we're gonna set at the end. Okay, so now this is the claim. If there is a beta balanced vertex min cut, like if there exists just one vertex min cut such that it's beta balanced, then you actually can find a vertex, like So sorry. I should say, you can find vertex mean cut. You can find a vertex mean cut in this minimax flow. So this is strictly less than n square if beta is big. Okay, so so that is the case that we are gonna show. Like if the X is a balanced cut, then you can solve it faster than n square max flow. And the idea is this. So let me assume that we assume that the X is this balanced vertex mean cut, right? So let's assume. So this is L star, S star, and R star. And you know, like if we get suppose somehow that I know X in L star and Y in R star, then I would be done actually. The reason is that first note that the cut size, like the minimum separator between X and Y, would be less than kappa, because this is a cut that separates X and Y too, right? Which means what? It means that if we compute max flow from X to R of compute minimum separator between X and Y, then you would get some cut, right? Which is a mean cut too.
But is it not equal?
Well, there might be some cut which is as small as S star, but it's not the same. So like you might get some so mean cut is not unique, right? So when you compute XY separator, you might get just some other cut, but of the same size, but not the same not the same cut, but the same size. Yeah, actually it must be the same, yeah. Right. Okay. So for example, if the graph is just a path, then this is like a balance cut, but if you give X and Y here, maybe the algorithm just give this as your mean cut. It's not the same thing as, it's just not exactly the same cut. Yeah.
But the size is same.
The size is the same, yeah.
Why is it? Sorry.
Oh, because we assume that kappa is the smallest vertex cut.
So we assume that cut is mean.
Kappa is like, yeah. So LSR is a vertex mean cut. Yeah. So if this is less at most kappa, then it must be equal. Yeah. Okay. So now you all agree, right? If we get somehow like some node in L star and some node in R star, we are done. That's all we need. But we just don't know where, like we don't know what is L star and R star. Like where is it? We don't know. So so now the idea is we want to construct some collection of pairs X and Y, such that at least one pair will one pair XY will be on the different side of a cut. So let me
But how do we know that kappa of X comma Y is equal to kappa?
Oh, because so first of all, kappa X and Y will be less at most kappa, right? Because X is here, Y is here. So if you delete S star, it would separate X and Y. So kappa XY is at most kappa.
Kappa is the size of the minimum cut, right? So
Yeah.
if you don't know anything about X and Y, it will be at least kappa S.
Yeah, so this direction is trivial.
Yeah.
This direction is by definition.
Yeah.
But if it turns out that X and Y, like this is true for every pair XY. But if X and Y are on the different side, then you would have other direction too.
Yeah.
All right. Okay. So, any more question?
Does it lead to randomized algorithm, like you can sample pairs of XOR?
Very good. Yeah. So actually, if it is balanced and if we allow randomization, yes, then it's going to be now quite easy to get X and Y. Yeah. Very good. Actually, let me ask you, like, how many pairs of X and Y, like, how many times you need to guess to get X such pair if you allow randomization? Yeah, something like n over beta, because
That's the probability of using one of the good ones and instead of the
right. So if we allow randomization, then if we pick y randomly, then with constant probability, it would be on the bigger side on R. So just constant time is you get that. And how many times you need to pick so that you get something in L is something like n over beta. So in total, it's something like O of n over beta, maybe times log n, just to make it with high probability. But okay. So just from here, actually, you see randomization, you can get like small number of max flow, even less than n. Yeah. But this is not clear at all for deterministic, right? How to do that. But we know that, okay, there is a trivial collection of pairs, which is all pairs. That's n squared. That's bad. But is there a better, like, better collection of pairs? So this is where Ramanujan graph is coming to play. Why? Because recall what is Ramanujan graph? It's just a graph such that when you look at any two set which is big enough, then there must be an edge between it, right? This is exactly what we want. So let's look at Ramanujan graph and look at the edge set of that Ramanujan graph and take the edge set of Ramanujan graph as your collection of pairs. So this is completely different graph, right? This is, you have your own graph G, and there is another expanded graph. Take the edge set of Ramanujan graph, and that is your collection of pair XY.
Just little above, there is n into n over beta. Is that deterministic max proposed or random?
N over beta? This?
Yeah.
This is going to be deterministic.
Deterministic.
Yeah.
So can it be also interpreted as like taking n over b vertices from left side and you choose all vertices on right side?
But we don't know where is left and right side, actually, right? We don't know L star and R star. Right? We don't know where it is.
Randomly, if we sample, we get n over beta, with n over beta samples, we will get one from left.
Okay.
So,
yeah, we are talking about, here is deterministic algorithm. Okay. Okay. So I want to recall again the property of Ramanujan graph. So from last lecture, we see that if H is Ramanujan, and D regular, degree is D, then actually if you take any set, L and R, we used to say S and T, but here we say L and R. If these two sets have large enough size, that is, if L times R times D is bigger than n squared, then there must exist an H between them. Okay. So, but what do we have in our situation? In our situation, we want that like, if L is bigger than beta, R is like O of n. We want that there should exist an H between these two sets. So how, like, then if we just set D to be something like NO beta, then there will exist, we know that there exists like D regular Ramanujan graph that guarantee this thing. Okay. So now we have graph, like graph H, such that if you look at any two set, L of size bigger than beta and R is bigger than n, or something like O of n, then there is an H between the two sets. Now we are basically done. So we just take each xy, take a pair xy where this is from an H defined by this expander, and compute kappa of xy, and return the minimum vertex cut that you have found. Okay. And you see one of the xy will be on the different side L and R. So yeah, so that gives you n times n over beta max flow calls. Okay, so that is like balance case. Question.
What's the relationship between the Ramanujan graph and the original?
Ramanujan graph and what, sorry?
The original graph.
It's completely different graph. So maybe like the same number of vertex, the same number of vertices. Yeah. So you have a graph of n node, then you take a Ramanujan graph of that have n nodes. Yeah.
Just a question about the state of the art you mentioned in the maximum flow. Are they deterministic or are they randomized?
So yeah, so this one is the state of the art for deterministic algorithm already.
No, the best.
The first one is randomized, like.
The time you need.
Oh, for max flow, I see. This is deterministic actually. This is randomized. Randomized.
I was trying to interpret the deterministic down you wrote down there.
Oh.
Plugging in the.
Oh, like they use like this bar is stated when the fastest max flow algorithm is not so fast yet. So I don't know if what like you just need to plug in the.
So they are already kind of like.
Yeah, but like I think the way to think about this problem is like how many max flow calls you need. Yeah. More question about balance case? Okay, so we go on. All right. So what if the mean cut is not balanced? Like we have no way to guarantee that the min cut must be balanced, right? And so here's a plan. The plan is that we will state some sufficient condition called a gap condition. And basically we will say that if the gap is large, then there must exist balanced min cut. That's the first thing we will show. And then we will show that there actually is a way such that given any graph, you can modify a graph somehow such that the gap becomes large. And once you have that, we just apply the argument for balance case. Okay. So now I will talk about the gap condition here. That if the gap is large, then there must exist balance min cut. Okay, here we already saw actually. So first, I will say that the gap is basically the gap between minimum degree, min degree, and kappa, min cut. So min degree is always at least min cut, but it might be much larger than min cut. So this gap, this is the gap. Yeah, I will call this the gap. And basically, we will see that every min cut must be as balanced as the gap. Like every min cut must be beta balanced, where beta is at least the gap. Okay. So if the gap is large, then you have balance cut. And actually, this is kind of easy to see by picture. So let's say that you have L, S, and R. So this is like a min cut. And let's just take any vertex X inside L. And we know that all of X neighbor must be either in the neighbor of X here, must be in L star or S star, just because you cannot have an edge to R star. Okay. So this is like how many guys are there how many black guys are there? Well, like these black guys are at least delta, right? But how many black guy can be in S star? It can be at most if it can be at most kappa. So if kappa is much smaller than delta, then this part must be big, right? So in math, we have that neighbor of X, the size of neighbor of X is at most L star plus S star. The S star is at most kappa. S star is exactly kappa. So L star must be at least the gap. Okay. So if the gap is large, you know that any min cut is balanced. Okay. And from now, the goal is to increase the gap somehow. And then we will want to apply the balance case. But to do this, we need to know a bit more about the problem, actually. So now we need some more structural lemma to increase the gap. And to do that, let me define one more thing. Kappa x. This is nothing but like you minimize kappa xy over all y. It's like a rooted connectivity, like smallest min cut that separate x from anyone. Okay. So clearly you can compute kappa x in nmax flow, right? So that is nothing. But now suppose somehow that you know that the rooted connectivity of x is strictly more than kappa. Then I will claim that kappa of g minus x is just kappa minus 1. So let's prove this. Well, first for the first direction, we have that if you delete just one node, you can reduce the size of the min cut by at most 1, right? So like, oh no, I mean this direction. Yeah. So you cannot you can reduce it by at most 1 if you delete one node. So this direction is easy.
Can we say that x is in the separator?
Yeah, it's first.
Yeah, we will have that actually. Yeah, next point. Yeah. So then good. Yeah, exactly that. So now we will say that okay. For other direction, we will say that okay. If you what? 1 sec. Maybe I missed the direction for both of them. Yeah, this is what I want to say. Yeah, right. So we want to say that if you remove x, then you know for sure that the size of min cut must reduce. And the reason is that if you take any min cut, actually it's necessary that x must be in the separator. Why is that? Well, because if you just take any min cut, LSR, but if x is not here, but if x is on L or R side, then yeah, you know that the kappa of x must be at most kappa, but that is not the case. Kappa of x is strictly more than kappa, so x must be here always. X must be here, and this is true for every min cut. So if you remove x, then the min cut must reduce by 1. Okay. So you remove x, the min cut reduced by 1, and the min cut cannot reduce by more than 1 too. So you know exactly that after you remove x, the size of the min cut is reduced by exactly 1. Okay. So this is like good to know. And how do we use it? So suppose that we have compute kappa x, all right, and maybe the corresponding min cut of size kappa x. And the way now I'm trying to describe the algorithm, right? So let's say that you really just compute kappa x. And you remember like the cut that you have found from kappa x as your best, cut you have found so far. If at the end it turns out that this is a min cut, then you would be done, right? You have found a minimum cut. But we don't know yet if this is the minimum one really yet. But you just remember what you have found so far. But if it turns, so if it is indeed a minimum cut, you're done. But if kappa x is strictly more than kappa, then you know something else too. That if you just delete x from the graph, then you have make progress by, you know that the vertex connectivity is reduced by 1. And if you recurse on the graph after removing x, you can recover the and you get an answer in the recursion. You can recover the original answer for the original graph G, right? So if you just want a number, you can just compute kappa of G minus x, and then you can return kappa G as kappa G minus x plus 1. Or if you want a cut itself, then you find a cut here, and then you just add x into your solution. Okay. And from now, let me actually denote kappa by the vertex connectivity of the current graph. All right. So that is when we say that, in particular, after removing x, kappa will be this thing. So we know that if you remove x and if you remove x, then kappa would decrease by 1, basically. Okay. So if we just use this, observation, we don't really do anything nice actually. That is, like, you compute single source MaxFlow, get kappa x, and remember the best cut, and then remove x, and then repeat it on other nodes. So, and do a single source MaxFlow again. So this in total will give you n square MaxFlow. It's not really nice yet, right? But the goal, recall that the goal is actually to increase the gap, not just to reduce the size of the number of vertices. And but so you see, if our goal is to increase the gap, which is delta minus kappa, when you remove x, kappa decreased by 1. So now I assume that let me just assume that like kappa x is strictly greater than kappa, because otherwise we are done, right? So let's assume that kappa x is more than kappa, and we remove x, so kappa reduced by 1. So the gap possibly increased now by 1 because this thing decreased. But the gap might not the gap might not really increase, right? Because delta might decrease as well at the same time. In particular, so let's say that this is x, this is its neighbor, and maybe there are a bunch of x neighbors such that its degree, if this guy x prime have degree delta, then if you remove x, then the degree of x prime here would be delta minus 1. So yeah, the gap doesn't you don't increase the gap. So the goal is now to fix this thing. To fix, by fixing I mean this. So let's say that F is a set of neighbor of X here, such that the degree of X prime become delta minus 1 after you remove X. So it's the one that you need to fix somehow. So what we will do is that we will do something to the graph such that, like, let's say these are the guy that need to be fixed. This is F. We will make them do something to the graph such that the degree of this become delta again. And once we can do that, then the gap would increase. You increase the gap, right? Is the plan clear? Okay. So now we will need another like lemma. Like we want to somehow to fix this thing, that is increase the degree of this guy in F, in the set F. And the lemma that we need is just here. It's gonna be simple. That is, if you take any pair xy, and if kappa xy is greater than kappa, then it's safe to just add an edge to the graph, and the vertex connectivity wouldn't change. And that is kind of easy to see, because basically we know that if you take any min cut LSR for any min cut for all of this thing, right? Take any min cut, you know that X and Y cannot be on the different side. It cannot be the case that you have X and Y here. It can be like X and Y are here, or X and Y are here, or all of them are in L star, or both of them are in R star. But if they are on the same side, like this, then if you add an edge here, it doesn't increase the cut size, right? So it's safe to just add this edge, and any min cut remains a min cut, doesn't change anything. But you can add an edge. Okay, so now with this lemma, we kind of have all the things we need. So recall the situation, okay? We have the graph with X, and these are the neighbor of X. And you remove X, and then there are some set here, call it F, such that each of these guys, the degree now become the degree of the guy in F. The degree after you remove X, right? The degree X prime. After you remove X, this thing is delta minus 1. Okay. So this is the situation we are now at. But what if, how do I fix this thing? How do I increase the degree of this guy in F? Well, suppose that I just choose any, one sec, do I have picture? No. Yeah. So suppose that I choose any node W, any node which is not X, yeah, any node at all. And then I compute kappa of W. Then there are two cases again, right? If kappa of W is kappa, then we are done. But otherwise, it will be greater than kappa. And then we know that actually if this is greater than kappa, then I actually know that even if I add edges from W to everyone else, it doesn't change the min cut. Just by this. Okay. But is this not the case that like W might already might be incident to a bunch of things already? Maybe it is these are like the neighbor of W from the beginning. So it only means that I can add this edge to fix this guy. The green guy will be fixed. But the guy that used to be the neighbor of W doesn't, I cannot add more edge. The edge is already there. Okay, so given W, I can define F sub W to be the one, to be the guy in the set that need to be fixed, but it's not incident to W. Okay. So this is these are the node that need to be fixed. Sorry, it's a node that need to be fixed, but not adjacent to W. But you see that we can, as we discussed, I can really add edge, this green edge, for everyone in FW. These are the guys that I can fix using W. So after I add this edge, then this node will have degree delta, and now they are fixed. Now the remaining step is that how many guys that I can fix with W. And the claim is that if I denote x g prime by the graph after removing x, then there must exist W such that I can fix a constant fraction of node in F. So I'm thinking like I can halve the number of nodes in F for each time that I choose W. So like the precise number is the guy that I can fix using W is at least F times 1 minus some fraction here. But you actually will see that the number of, we will see later actually that the number of nodes in G prime, the graph that we work with for the whole algorithm will never be more, never be smaller than n minus root n. And we assume this. So given these two things, we would have that FW would be a bit bigger than F. It's at least constant fraction of F. Okay. And you agree that once we have this, we are kind of done now. We can just keep fixing F, a constant fraction of F, again and again. And after log n many W, you can fix everything.
So the purpose of having this lemma is because we can have a faster computation.
Yeah.
So we do the rooted
We want to reduce the number of computing rooted max flow.
So
We want to say that just by choosing W1, W2 up to W log n, then you fix all the thing. That cause you fix all the problem from X by choosing a log n more W.
so if we only consider the number of pairwise vertex cut, then we don't need this lemma, right? We can just pick for every those nodes that do not achieve the minimum degree. We just pair that with arbitrary non-adjacent vertex, and that's still at most n of them.
Oh, one sec. Yeah.
So we don't have to use this lemma, but this lemma
Let me think.
leads us to a.
One sec. No, what? Because you're right. You are right. So actually, good point. Yeah. So you mean I just try to rephrase what Chang'an said. So if this is the neighbor of X, and this is the set that need to be fixed. And what we can do is literally just for each of this node here, just look at non-neighbor of this node. X7 prime. Then compute max flow between X prime and X7 prime. And if it is like a kappa, if this is kappa, then you're done. Otherwise, you can just add an edge here, and you would fix this guy. So you can actually fix each of this in you can fix all of this in F minimax flow. Yeah, good point. Yeah, you're right. So yeah, so this is I see.
But we need this because we have a faster.
Yeah, that was that it is you do it this way. They do it this way in this paper because there is a faster algorithm for single source max flow.
So in that case, you can do a larger beta. Take the beta larger than.
So the fastest single source max flow is still MN. So you cannot go beyond that. We don't know how to go beyond that yet, basically. Good, but maybe there is a better rooted. There might be an algorithm which is better than do it to solve single source rooted connectivity from W. Maybe there you can do it better than N max flow. That makes sense. Yeah. So is everyone with me here that actually forget this thing first. If you just want to fix everything in F, then F max flow is enough. For each of the guy that need to be fixed, X prime, you just choose non-neighbor of it. Choose the node X7 prime such that there is no edge between it. And then compute max flow between them. Yeah. And if this is true, then you are done. Otherwise, you add an edge and you fix it. So and you do this for everyone in F, so you just need F minimax flow. Right.
How do we always check with the kappa? So how do we know the exact minimum kappa?
We don't know, but the point is that we will just remember all the time, all the cut that you have found. And because you always remember all the cut that you have found, you can just assume that this is not kappa yet. But at the end, at the like last step, you return the minimum cut that you have found so far too. Yeah. Okay.
So irrespective, because we don't know whether the kappa is there, we just find a non-neighbor and add an edge.
Yeah.
But we also store the max.
Yeah, you need to compute max flow too. Yeah. Okay.
Do we have a factor n of the last thing we were talking about? Like, we can find a non-neighbor of x, but is there a guarantee that, like,
Oh, you mean how fast can you find non-neighbor of a node?
Yeah, because delta is last.
So, well, we can kind of. So this can be done like in like if you can basically maybe scan all the neighbor of yours and take any node which is not in your list. So for each x, you look at all of the neighbor of x, and maybe take any node which is not in your neighbor. So that takes like degree time to get non-neighbor.
okay, but what if there is non-neighbor like of x such that the cut between x and the non-neighbor is kappa?
Oh, because when you choose, you have x. Sorry, maybe you call it x prime. So just to, you have x prime and you choose non-neighbor x double prime. And and you always compute max flow between them, right? So if the max flow between them is kappa, then you would be done. You just remember the cut between them that you have found. And otherwise, you add an edge between them.
So what if there is other non-neighbor of x such that make the main cut of x and x prime not kappa, but we just found a particular non-neighbor?
So note that here all we want to do here is not about removing x, all right? What we want to do here is just to fix the degree of this guy, like to make the degree become delta. So it's just really enough to just find, like for each of this guy, x prime, just really enough to just find one node, such that it's just safe to add one edge between them. Yeah.
Essentially, any non-neighbor will do, and you just remember the cut size and finally take a mean.
Yeah. Yeah. Okay. So so let me come back to the like more clumsy algorithm, which is I choose W and compute rooted like to compute kappa W, and then we claim that there must exist one W such that just from this one you can fix a lot of things. But that actually is kind of easy to get because like there must exist a guy that is good. Why is that? Because well, if you look at this graph, this is x, and call this g prime, which is after you remove x, and this is the thing that need to be fixed. The total degree of f in g prime is small, like because they have degree at most delta minus 1 here. So each of them have degree delta minus 1, but just because of this, they must, just by averaging argument, they must exist just one node, such that the number of edges from W to F is at most this. At most this thing over this. Okay. And so because W is adjacent to this many nodes in F, then the number of nodes which is non-adjacent to W is at least this. And which means that you can fix a lot of things using W. Okay. All right. So now, yeah, now I'm gonna summarize the algorithm very soon, but just like you will see that like in the algorithm, the number of nodes in the graph that we work with is gonna be big always, and we assume this. So that like, and if we keep finding W such that you fix a lot of things, like constant fraction of it, then just log n many times of choosing W, you will fix everything. So now the algorithm is just here. This is the algorithm for unbalanced case, which is, you should think of it as a reduction to balanced case. It's not like there is no two case. You should start by assuming that the graph, the mean cut is unbalanced, and try to fix it somehow. So what you do, choose any node X, compute kappa X, and remove it. Okay. And then let F to be the guy that you need to fix, and then find W that you can fix a lot of them. And then compute kappa W. And then you keep remembering the thing that you have found so far. And then you fix everything in FW by adding an edge between them. You know that this will happen log n many steps. So if you have done all this, you know that at this point, kappa X that you have compute here, and the best cut from kappa W, but you need to plus 1 because it's the graph. This is the thing after you remove X. These are the candidate answer for your kappa. And so you keep this as your candidate always, but you have increased the gap now by 1. And all of this step, you only need something like n log n max flow. Right? And note that this is actually a very interesting problem. That is, can you take little of n max flow to compute kappa X? If you can, it would immediately improve this. Right? So this is like a, yeah, open, very nice. Okay. But yeah, and now, so all of this n log n max flow, you have increased the gap by 1. And if you repeat the like increasing the gap, but like repeat this whole process by, let's say, delta time, then it would be like at the end, the resulting graph would be beta balanced. So to conclude, if I just call the gap increasing procedure for beta many rounds, that takes beta times n log n max flow. And now you have a balance case. And for that case, you take this many max flow. So by choosing data to be root n, then you're done. So that's the algorithm. And yeah, so it would be very interesting if we can reduce the number of max flow call. So this is like one very concrete thing to think about. Yeah, just getting anything actually below n to the 1.5 would be very nice. Or getting n would be very good too. So for a randomized case, it's like so far much faster. So I think something should be possible for deterministic case. Like the gap shouldn't be this large. It's strange. By the way, there is an interesting open problem too in weighted case. So the same problem where each node have weight, and you want to find the minimum weight min cut, vertex min cut. The problem is clear, right? You want to find a set such that the total weight is smallest. You separate the graph. Yeah. In the weighted case, the base algorithm is something like MN, randomized. The base deterministic algorithm is M square. But if the graph is dense, then basically this is n cubed and n to the fourth. Yeah. So, but if you just care about number of max flow call, in the randomized setting, you can actually do it in like basically this basically is about like using n max flow, and this is not like precise, but roughly speaking, this is like n max flow and this is n square max flow. So getting any improvement would be interesting here too.
Are those max flow mean possible? Just regular?
It's just about max flow, just capacitated max flow. So each node have some capacity.
Correspond to the weights.
Yeah, right. Okay. Or actually, is it actually hard? Is there like some fine-grained complexity reduction possible to show that, like, let's say, if you can, I kind of believe that it should be hard. It shouldn't be linear, but I don't know really. Like, it seems like if it seems to be harder than some matrix multiplication problem, yeah. But I'm not sure. Yeah.
Is there a proof that reduction to matrix?
I don't know. I don't have it. I don't know. But I think there might be. Yeah. Okay. So, any question about vertex min cut? Yeah. So basically, like, if I need to say, like, the state of the art of graph algorithm right now is that in undirected graph, it's quite easy. Like, a lot of things become nonlinear now. For directed graph, a lot of things are still hard. And actually, the thing that is easy in undirected graph is about edge cut. And now with the vertex cut is something in between the two. Like, I can make this precise, but it's something in between the two things. And it's not clear for both directions, like, is this the hard thing or easy thing in here? So, like, a lot of interesting actually is going on here. So, yeah. So now for the next class, it's going to be the last characterization of expander. We will see like a probabilistic view of expander. That is, for example, actually, if your graph is if the graph is a complete graph, let's say it's a clique, and you are at one node x, how would you, what if you want to go to the random node, then you can just take one step of random walk, right? And you get to a random, uniformly random node. If the graph is a path, it's not an expander. To take the step, you might need to do a random walk so many times to say that right now you are at a random node. Maybe like n squared rounds. But if the graph is an expander, turns out that you just need something like log n, many random walk steps. So we will see that, yeah. And we will see that knowing this, you get like a cool algorithm from it. Yeah. For example, if you have a graph and you have two nodes, and you want to find a short path between them, you can do it in square root n time, so sublinear time of a graph. So we'll see that next week. Okay, thanks.
So there is an in-person discussion session?
Sorry?
Tomorrow there is in-person discussion session?
Yeah, there is. Yeah, tomorrow. Yeah.
I'm still confused about
Sure.
this procedure. Like, if we want to fix this, so to fix it, we need to find a non-neighbor such that this node is here and this non-neighbor should be here.